This fourth lecture on the divergence theorem is about using it as a mathematical tool to derive another famous equation in physics, the heat equation. So this is Joseph Fourier, who discovered the equation in terms of its modeling and the solution to the partial equation. I should give credit to Wikipedia for the photo. Fourier wrote this important treatise more than 200 years ago, in 1807. I don't understand French, but the title says something like the propagation of heat in solid bodies. For your perspective, the divergence theorem was discovered by Lagrange 45 years before this treatise in 1762, so vector calculus is well developed back then. The focus of many mathematicians during this era was in discovering equations that relate to physics. I don't know again this French text, but this is how Fourier wrote the heat equation. This looks like the Greek letter nu, where nu is temperature. So nu is a scalar field in terms of x, y, z, and t. So you have the spatial domain and the time domains. You can see that this field exists in two domains. Again, domain for the space and the domain for time. Now this is an important example of a balance equation. The heat equation states that the first order change in temperature with respect to time equals to the second order change in the temperature with respect to its location. So we have the left-hand side being balanced by the right-hand side. Today we have these common forms of the heat equation. You should be familiar with this short form. We call it the Laplacian to refer to these second-order partial derivatives. You should be familiar with this form, and I would say that it's just a review for you. Another important form is the bottom one, where we bring the right-hand side to the left-hand side, where the new left-hand side is now equal 0, and this is very useful when later on we deal with the numerical solution to this partial differential equation. And the new right-hand side, whether it's 0 or not, gives us a new interpretation regarding the source of heat in our modeling. To start the analysis of heat propagation, we need to be familiar of these material properties. So we have thermoconductivity K, density rho, and specific heat of solid sigma. And here you can see various materials. For example, diamond conducts heat much better than copper, although we use copper everywhere, right? I think you know why. There are different perspectives in how to analyze the change in heat that a solid object contains. So in this case, we are looking at the change inside the volume over time. So we want to quantify how it changes as time changes. If you imagine a volume like this, the state of the heat change or the state of heat changes over time inside the volume. To describe the change, we need to mathematically quantify what we actually mean by heat. And this is what we do in mathematical modeling. We want to be precise in our definition. First, we assume heat is leaving this volume. That means Q is decreasing with time. Now step 1 of the analysis goes like this. Define heat Q, and we know this from physics of heat transfer, and we have this definition. Heat Q is the volume integral of certain quantities. It includes the material properties that you just saw. The integral tells us it is total or net quantity. On the right hand side, we have these three parameters. So rho, sigma, and U. U is temperature in Kelvin. Then you have rho as density and sigma as the specific heat. Now just for a quick check of their units, we can see that some of them simply cancel out, and we are left with joule per meter cubed. So in a sense, you can think about the integrand being as the heat density. So if you imagine the temperature U varies throughout the volume, and you have the scalar field U, and you also have the scalar field of heat density in the volume. Now we describe the rate of change with respect to time. It's pretty straightforward. The rate of change is what the derivative is. So that's standard calculus here. So we have Q as a function of time. You should see that Q is no longer has the coordinate, right? It's because we are integrating it, and the result is just as a function of time. Because of the assumption, we have the negative sign. In other words, the rate of heat loss. See, we said earlier heat is living, now we have heat loss. This is important in mathematical modeling. We need to make an assumption to simplify equations. So we assume rho and sigma to be constants. Then we don't want to take the derivatives, otherwise we get 0. So we just bring them out. Now it greatly simplifies this equation. Only the temperature U now takes the derivative. U is a scalar field that is also varying over time, so that's why you see it as being partial derivative. We will use this form. This is the first form that is going to be used later on in part 2, where we will look at another perspective of heat change.